Okay, the next step is looking on the differentiation part of a controller, because the idea is we have seen that in the integrator case with a very large negative phase, -90, the closed loop is very slow. With the PI, we have an acceleration because the phase is not so negative. So we see negative phase make a closed loop slow. Question is, can positive phase not make a closed loop fast? And the idea is correct, but to find a good controller type is not so easy, because here you see the D is an indication for differentiation, and here you see in the phase curve that really there is a part in the frequency range where we have a large positive phase. So could we use an acceleration by these blocks? The answer is no. Block 6, 7, and 8 contains a transfer function with a P, the naked P in the numerator. That means in DC case the gain is 0, and gain 0 in DC case means control error 100%. That means cruise control in a car with an activated D or DT1 or DT2 controller will stop. So that's not really that what we want. So we look further on and we see, okay, there are block 11 to 14 with a D in the name. Really, if you look on the phase, there are frequency parts with positive phase. So question, can we use these blocks? Yes, we can, because the DC gain is not 0, is larger than 0, so we have a control error which is not 100%, which is smaller. And the idea is, so let's start with a PD or PDT1 controller. In the student paper some years ago, I have also added the PD part, but I have cancelled it because this is just a theoretical idea to think, can a PD accelerate a closed loop system? Of course it can, but you cannot build it because a realistic PD is not possible. If you realize a PD, you get always a PDT1. So I think it is much better to just look, can a PDT1 accelerate my process? PDT1, here you can see, is this transfer function. We have a positive region with positive phase, and the idea to work with a PDT1 controller comes now in this next chapter. It should be chapter 5.2.7. 5.2.7 PDT1 controller. Idea: positive phase can accelerate closed loops. And this is really true. You will see in the result, this is really an idea to have fast closed loop systems. The transfer function of this controller is a KC. Then we have a 1 plus P, D, and D in the numerator, and a 1 plus P. I express now the time constant of the PDT1 with the step depth. Yeah, step depth is the well-known ratio of numerator and denominator time constant. And we have worked with the step depth also in project 2 with the temperature control system. You have here in the transfer function, in the controller, you have a KC, and of course the KC will be calculated with the same method than before, using the Nyquist magnitude equation. You have TD and a step depth. So you have to select, to choose TD and step depth value, and I will help you how to do this in a good way. if you look on the phase curve of the PDT1, then we have a phase maximum, a positive phase maximum here in this region. If we analyze this in more detail, then we can say, okay, nearly at this position, we have the corner frequency 1 over TD, and here we have the corner frequency step depth over TD. So the step depth defines the size of the magnitude of the maximum of the positive phase, and the distance between both corner frequencies. And TD defines the position of this curve on the frequency scale. The question is, what is a good position? Answer is, the good position is if we can realize a controller in that way that the crossover frequency with the phase margin is exactly at this position. Problem in this decision is the crossover frequency is a result of the design, and before you get omega d, you have to define TD. So we get an iterative process because we have to select a value before we have results. The experience shows that a good selection of TD comes with again with pole compensation, and I will show you how this works. Pole compensation, in that case, that TD, note that we have done this in the temperature controlled system, that the differentiating time constant, the TV in that case, was set to the second largest process time constant. And exactly this gives further acceptable values. Okay. So we can say selection of TD, in our case 0.33 seconds, second largest process time constant. Later, see below with hints for this selection. I give you a table depending on the type of the process, is how to do this selection in a good way. And finally, I show you a method where you don't know, normally you don't know the time constant of the process. If you have a Bode plot, how to work just with the information of the Bode plot of the process to get a good selection. Yeah. Okay, in our case, we have a good selection because the time constants are known, and we select TD is 0.33 seconds. And yeah, what about the step depths? You should know step depths should be in the range of, 1 is no step depth, so it's no acceleration. Between step depths, between 5 to maximum 10. The value of the step depth gives the acceleration factor, but note that any acceleration of the loop means actuator amplitudes will increase, and if you select a too large value of step depth, then you have very big effects of limitation of the actuator output. This is a nonlinear effect which can cause other nonlinear problems. So the selection should be not too large. 10 is maximum selection. Any step depth which is larger than 10 is not good. Okay, in this case we now can define the following Bode plot. If we have selected a step depth in my selection, I show you in workbook what happens if I go to step depth 10. Then I can add the phase of the controller. Add phi which is arc tangent omega TD, positive part of the phase, minus arc tangent omega TD divided by step depth. That's a negative part. So this is a phase equation, and now the task is, and this is of course a little bit uncomfortable, to calculate these values for some omegas and add to the phase curve of the process. To phase curve process. And you see this in workbook page, I think this is 40, I have to look. Yeah, the bottom part of page 40 in the workbook. So I switch to the workbook, and here you see that time constant, as shown in my paper, is selected to 0.33, the second largest process time constant. I have selected a step depth value of 10, and with this phase equation I get a new green curve. The green curve is the phase of the open loop, including process phase, that's the red curve, and the positive values of the PD controller. So the difference from this point to the green curve, from red curve to the green curve, is a positive phase of my PD controller. And at once you can see with the same phase margin value, this is minus 120. So up to minus 180 we have 60 degree phase margin. This distance, 60 degrees phase margin. This was a P controller phase margin, omega D value, 2.6. Now you can see our new crossover frequency ends up in 7.2, around 7.2. So we are 3 times faster than a P controller. The resulting values are listed here on the page 41. Omega D is 7.3 per second, and the rest is unchanged. Rest is not new. Result: omega D is 7.3 per second, so about 3 times faster than a P controller. That of course we want to see in our simulation. So with omega D we have now the only thing what is missing is Kc. Again, Kc with the magnitude equation of Nyquist, that the total open loop gain at our now calculated omega D crossover frequency is 1. The compartments of the open loop is the controller magnitude, and the controller magnitude can be calculated as done several times before, with the magnitude of the numerator of this transfer function is 1 plus omega D TD squared, and in the denominator we have the square root of 1 plus omega D TD divided by step depth squared, multiplied with the process magnitude value at omega D, which has to be selected out of the diagram. We go back into the diagram, and here we can see if we look at this crossover frequency up to my cross point of the process magnitude curve, which is the blue curve, then we see that is nearly very good, negative 20 dB. My value is here in the exact paper with cursor function in my simulator. This is 20.2, but in my calculation now I just work with negative 20 dB, which is a very simple value. Negative 20 dB is equivalent to 0.1, and this equation then can be solved to Kc, and finally you get a Kc value, which is paper value is 4. Kc is 4. Okay, this can be simulated in my simulator. I start the simulation with a 4PT1 process and with a PDT1 controller with gain 4 and TD 0.33 second and step depth 10. Wait for this simulation. I have to restart this because last week I've closed this picture, so I have to redo P controller and PI controller with pole compensation. Then you get a third curve with this controller. Now I'm here in the simulator and look for these both curves. The blue curve was the P controller with 60-degree phase margin. The red curve is the PI controller. So these are the well-known diagrams of last videos. Now I replace the PI with the PDT1. It is poor that at this time no single block is for the PDT1, is prepared for the PDT1. Of course, you can make a PIDT1 to a PDT1. This I should do. I can show you now, but of course you can also combine a PD in series with a PT1. But then we have two blocks, and then I have to do this. I think I should do this both. I remove the PI controller. Then I make a PD block. The PD block has our gain 4 and time constant 0.33 seconds. And I add a PT1 with the block gain 1 and TD divided by step depth. So this is 1/10 of the 0.33 seconds. So this is now my PD, and you see the series connection has now to be put into this diagram. It's not so nice, but possible. Donald Duck technique. And this should now work. Let's check. I calculate now the new curve, and you see here much faster than P. What you can see here is more accuracy, but not high accuracy. More accuracy because the gain K is larger. It's 4 instead of 2. So we are now has a control error. I just should add in my paper here. If I just quickly select the XD of infinitely large, time is 1 divided by 1 plus a DC gain of the process. Process at 0 multiplied with controller at 0. That was the equation. And if we fill in our numbers, we get 1 plus process DC gain is 2 and controller DC gain is what you see is here our 4. So we have 1 divided by 9 equivalent to 11%. And if you see in my simulation, this is 11% different from 1. We get here an 0.89. And we are much faster. So we can see here our peak is at 1 second. And this peak is just faster if we measure the time with my coordinate cross. And we see this is just 1/3. If this is 1 second, this is 0.35. This is 1/3, 3 times faster. This is also the factor 3, also calculated by the 3 times larger crossover frequency. Okay. Now I show you how I can change a PIDT1 block into a PDT1 block, because this is block is available in my simulator block reg, but you can do this in any other program or system where a PDT1 is available. For example, in SPS computers, there are blocks of PID controllers, and if you need a pure PD without I, of course you can use this. You have only to do the following step. Note that the transfer function of a PDT1 is KC1 plus PTN 1 plus PTV divided by PTN, and this is 1 plus PTV over step depth. That is the Bode form of the PDT1. And the question is, how can I remove this? Just the idea is make TN very large. Mathematically infinity, but this is in numerical systems, it's not possible. So say 10 to the power of 10 or so. Make it very large. Then this one can be neglectable, and then you see PTN and PTN can be deleted. And you have the last final expression where TV and TD is the same factor. So let's do this quickly in my simulation. And then you will see same curve. So I remove now block 5, block 6. I remove these branches and I add a PDT1 controller with proportional gain 4. PI time constant is infinity. TD time constant 0.33, step depth 10. And this block should work in the same way as we have seen it with our two previous blocks. So I just come here, I store this, and the new curve should be black, and you see not identical but very similar. If I increase here this number of points, then both curves will be the same. But I think you see the controller and the PDT1 controller with very large TN, and the two blocks PD and PT1 together in series gives the same behavior. Okay,